It's a great pleasure to be here, and I am debating what to talk about. I recognize there might be a number of chemical engineers and material scientists in addition to chemists, and so I'm going to try to span that broad cross-section. My background's actually in catalysis, and I thought if I go into gory detail of every reaction mechanism, I'm going to lose about half the audience. So I'm going to show you pictures of the catalyst and tell you in a couple of cases kind of how we design them. But I'm really going to give you an overview of what we can do with these catalysts, and I think for a broad audience that might be a little more interesting. So let me get started here. I entitled this "In Pursuit of the Perfect Plastic." I thought the perfect part sounded very intriguing. The reality is we're not even close to getting there. So the pursuit part is particularly important to remember. So with that said, I think plastics. We got plastic plates, cups. You could argue that we have a lot of perfect plastics already. They have properties that are truly spectacular over a wide range of applications. One, and I've tried to draw some pictures up here that where plastics are used, and I always get the question, why is the baby plastic? It's the diaper. So I don't know if Nathan's out there. He has a new baby, but all these, whether it be a windmill, single-use plastics, they're used in electronics. I don't have to tell you where plastics are. It'd be a totally different world if we didn't have these materials. So they're perfect already. What's not perfect is how we make them. So it takes a lot of energy to make these materials. Typically takes fossil fuel, which is not a limitless resource. And we also we use them sometimes for a matter of minutes, and then we throw them away. Like these plastic plates here. And often if these plates, you probably, every time you open up CNE News, in fact, there was just a recent cover showing all the plastic waste and how are we going to deal with that in the future as polymers grow at about 6 to 7% per year. So we really need to think about where plastics come from and where they go, not just how great they are when we're using them. So this next slide goes into a little bit more detail on this. And so I entitled this "In Pursuit of the Perfect Plastic." First thing we are going to want to do is get away from fossil fuel as a building block for making plastics. We really need to start thinking about the lifetime of the polymer. If we use that plate for a half an hour to an hour, if it gets into the environment, it's going to float around in the ocean for a decade or a century. Do we really need to have materials for such short use, persist in the environment for such a long period of time? We want to start thinking about ways to make plastics that use less energy and raw materials. A lot of the current, there are a number of biodegradable plastics, but they use even more fossil fuel than non-degradable plastics like polyethylene and polypropylene. And so thinking about how we make these plastics is also going to be really important. I would say, at this point, if you can come up with a material that meets these three criteria, you're doing really well. But the reality is that we have a couple more that we need to worry about. The next is if you make a new-to-the-world polymer that maybe it's made from renewables and it falls apart in the environment, but say it's a plate and you pick it up to put a cookie on it and it cracks in half, nobody's going to want to use that. And a lot of the materials that we have that are trying to replace the tried and true plastics don't have the performance that we want. And the final one, you're probably wondering what the final one is. Well, ultimately, these plates are probably about 50 cents a pound. These are plastics that have been made for over half a century. They're incredibly inexpensive, and if you make some cool new plate that has all these other constraints, but it costs 2 or 3 or 5 times as much money, people are not going to want to buy it. So the hope is that somewhere in the middle of all these that there is some magic material that takes into account all 5 of these. I would say if you can hit 3 of them, you're doing pretty good. And so today in my talk, I'm going to tell you about some of the work that we've done to try to address some of these issues. All right, so starting out, we've decided as a building block that we wanted to use carbon dioxide and carbon monoxide. And first off, these are incredibly inexpensive compounds. In fact, if you sequester CO2, they'll actually pay you a small credit if you use it. So instead of starting out with something that's quite expensive, these are very attractive. You can get these from multiple sources. You can get them from fossil fuel. Of course, it'd be a lot more interesting to get these from biomass. Or you can get CO2. You can actually get it from the earth. There are parts of the United States where you can actually tap, like in Colorado, and pull out CO2. And so these are feedstocks that are plentifully available. It'd be hard to imagine how you could actually build these into a linear polymer backbone without making a carbonate or making an ester or making a sort of linkage that we know through organic chemistry would undergo hydrolysis and degradation a lot faster than a hydrocarbon polymer like polyethylene. And so the real challenge here from a basic science standpoint is that these molecules are fairly stable and they don't have the driving force that we typically like for an efficient reaction, especially in a polymerization. Okay, so back to the kind of the Venn diagram, you immediately start to address the transition from fossil fuels, especially if you can use CO2. Water gas shift chemistry, there are commercial units you can buy if you have CO2. You can reduce that to CO. And so you can immediately get these from renewable feedstocks. And I'll show you an example where we actually took CO2 off an ethanol fermentation on the commercial scale to make one of our plastics. As I mentioned, these are going to build units in the backbone that should facilitate biological degradation. And being that they're really, really cheap, if we can put a reasonable amount of these molecules into the polymer, it should make them relatively inexpensive so they would compete with other types of plastics. What remains is, can we make these? Can we make them at all, and can we make them efficiently? And then if we make some new to the world material with these molecules, can we get properties that people are going to want to buy? So I'm going to tell you a few different types of polymers that we've made with this in mind. And starting out is a polymer that we've made from carbon dioxide. Of course, it'd be great if you could just make poly-CO2. You can do calculations on that, and that would spontaneously depolymerize back into CO2. But you can use an epoxide like propylene oxide and end up with a polymer structure where the epoxide and the CO2 alternates in the polymer backbone. The catalyst that we developed is based on a cobalt salen. It's activated by an ionic species. These are interesting catalysts because they work at very low pressures. You can actually put a balloon of CO2 on the top. You don't have to use really high pressures of carbon dioxide. The polymerization is very clean. There is a possibility that you make the cyclic product here called propylene carbonate, and that's actually the thermodynamic preferred product. The polymer is a kinetic product. And so we need a catalyst that can very cleanly make polymer and not cyclics. We can make really high molecular weight. We can control the stereostructure of the polymer. And so at the time we developed these catalysts, these were by far the most active and selective catalysts for polymerization of propylene oxide and CO2. And people had already worked out that the polymers have really good barrier properties. So for food applications, they keep oxygen out of the food, or if you have, say, carbonated water or beer, keep CO2 in the package. You can use them for lost foam casting, a way to make metal objects like an engine. You can use them as a sacrificial material in electronics. My understanding is that the polymers that we make are now currently used in a number of electronics. And to do this, you need really high molecular weight, and we've been able to do that. The problem here is that these markets are pretty short-lived. Here you actually burn the plastic in making the electronic, so that kind of defeats the whole purpose of making these. They're also very small markets, and so we want things that are going to be used on the large scale to replace the fossil fuel-based plastics. And so some of the ideas that we had were can liner materials. There's a plastic inside all food and beverage cans that protects the food from the metal can. Polyurethane insulations, polyurethane, you're sitting on a polyurethane seat cushion, same thing in your automobile. So polyurethanes are really important, and this whole field of architectural coatings. And to make these, what you need is a polymer that's lower molecular weight, and on the ends of the polymer are these alcohol in groups. So you can throw in a diisocyanate, and by kind of old-fashioned step growth polymerization, you can build the polyurethane. And so at the time we started this research, nobody had ever made these. They've, of course, the seat you're sitting on is where you just take propylene oxide and make a homopolymer propylene oxide with alcohol in groups. Here we wanted to put in CO2 into the backbone of the polymer. Okay, So I'm going to really simplify what we did. The idea was develop a catalyst that allows an alcoholysis reaction. So if we're growing a polymer chain off our cobalt, and we need to have an alcohol that can come in and react, and now this alcohol can grow a chain while this one's dormant. And if this process is really fast, the idea is that we start out with a diol. You can also start with a triol or a tetraol if you want to make higher functionality polymers. We add in our catalyst, and when the catalyst activates the alcohol, we grow the polypropylene carbonate. And eventually another alcohol comes over and it does this alcoholysis process, and it reveals the alcohol in group, and it goes off to another molecule of diol. So by the stoichiometry of the reaction, you can slowly add propylene oxide to and CO2 to the ends of the polymer. We make polymers that have the maximum amount of carbon dioxide. Here with propylene oxide, it's about 43 weight percent. So ethylene oxide is exactly 50 weight percent of the polymer. And the alcohols that start out on the diol end up at the ends of the polymer structure. So we get very high levels of alcohol functionality, which is vital if you're going to make high molecular weight polyurethanes. You need to have at least 2 alcohols on each end of the molecule. So as Chad mentioned, we started a company called Novomer, and Novomer was able to scale this technology, and this is now almost 5 years ago. We were able to make many tons of this material down in South Carolina at a company called Albemarle, and they have a process where they make ethanol on site, and they were able to take the CO2 from that process that would have been vented into the atmosphere, run it through a dryer to get out the water, and basically pump it right into this reaction. And so the polymers we're making here actually captured carbon dioxide from the reaction. So we made, this first run, we made about 7 tons of the polyol, and we're really excited because now we had samples that when people wanted to come and see how our polymer worked in their application, we'd have samples to give them. And so then the sad story is about 2 years later, we still had, I think it was like 6.99 tons of polyol. We were able to give out some samples, but not as much interest. We were hoping that within months everybody would make car seats out of our polymer. And we had drums of this, 55-gallon drums of this stuff kind of sitting around. We were thinking like, man, it's going to be a lot of money to go dispose of this stuff. So, but if you start a company, I guess my advice is be patient. Things don't move fast, at least in most companies. So eventually, so this is in 2016, we got this really cryptic call from Ford, and they said, hey, there's going to be a press release, don't tell anybody, but we're going to announce that we're going to start using your polyols in our Ford automobiles. And so what you may or may not know that there's a lot of foam in a vehicle, not just in the seats, but in all portions of the doors and the panels for sound deadening. And each vehicle has about 30 pounds of polyurethane foam, and most of that is based on the polyol. And so Bill Ford, this was a press release, said that they're going to start basically in all sorts of different parts of the car, start using these CO2-based polyols. And I think the plan then was 2020 or 2022. So ask me in a couple years if they're actually doing it. But they were planning this would save around 600 million pounds per year of fossil fuel just for automobiles alone. So if you start thinking about sofas and chairs and all the other things that use polyurethane foams, I think it sounds really interesting that people might start adopting these. Surprisingly enough, the properties are way better than a normal cushion. They keep their resiliency better and are obviously going to be a lot cheaper because they're largely made out of CO2. So Novomer was able to transition. They sold the technology to Aramco, and they've announced that they're starting to build the first world-scale plant for this that hopefully will be supplying companies like Ford. I want to go off and tell you a little bit about some other types of polymers in this area. So that polypropylene carbonate, if I gave you a sample of it, just the heat from your hand would start to kind of soften it. And for most polymer applications, you want something that isn't going to soften until well past the boiling point of water. So you'd want a melting point or a softening point, a glass transition temperature of 100 degrees or higher. And the other thing that you might have nicely not said anything about is like, isn't that propylene oxide made from propylene, which is made from fossil fuel? And so we thought it'd be great to try to find a natural source of alkenes that we could use to make an epoxide. And we started looking at limonene, which is it's a byproduct of the orange juice industry. You can actually, just from the orange juice industry, there are hundreds of millions of pounds of this made every year. You can also get it from the catalytic isomerization of pinene, which comes from the paper pulp industry. So there are multiple ways to get this molecule. And again, I would love to give you a half an hour lecture on how we came up with this catalyst that is, to my knowledge, the most active and the very first catalyst that was able to polymerize limonene oxide and CO2. But instead of talking about the catalyst, there's some interesting features of the stereochemistry of this polymer. Given that oranges, they have a stereocenter here, and so you build in the stereocenter here, and then the epoxidation, you can control that to give either cis or trans. And then when you do the ring opening of the epoxide, you invert the stereocenter at the site of attack. And so this polymer is perfectly stereoregular. All the stereocenters are dictated by that original stereocenter up here on the limonene molecule. The polymer properties, this has a softening point, a glass transition temperature of about 120 degrees Celsius, which is higher than that of polystyrene. And so you can think about making things out of this that you currently make out of polystyrene. The kind of the neat feature of this polymer, you probably accidentally got a polystyrene container next to your toaster oven and it smells really bad like styrene. These polymers smell like oranges if you heat them up too much. So they do fall apart, but they at least smell good when they do that. And so I want to show you some neat things with the stereochemistry of this polymer. So from oranges, you can get the R isomer, and from various types of pine trees, you can get the S isomer. So these are now mirror images of one another. And this is a modified version of our catalyst that takes CO2, and the R gives poly-R-limonene carbonate, the S gives poly-S-limonene carbonate. And as you'd expect, the properties of these polymers, except for how they rotate plane polarized light, are identical because they're just mirror images of one another. And like with small molecules, you probably remember from organic chemistry that if you make a small molecule and you crystallize it and you look at the enantiopure form and then you look at the racemic form, not always, but often the racemate has a different melting point. It's often a more dense crystal and a higher melting point. And like with polymers, we wondered, what would these do if you mix these two together? Surprisingly to us, even though this is a perfectly stereoregular polymer, the polymer does not crystallize. Okay, most polymers that have careful control of stereochemistry, like polypropylene, is a semicrystalline polymer. And so we were a little disappointed that this was an amorphous, non-crystalline polymer. So we thought, well, maybe if we mix them together, maybe it just mixes randomly and it's still amorphous, but maybe there's a chance that it makes what's called a stereocomplex, where the two enantiomers together can interact in a way that you can't do if you only have one enantiomer of the polymer present. And so I want to show you a simple experiment. You can dissolve these polymers up, and these are 1 weight percent in hexanes, so very dilute solutions. And we're simply going to mix the two together. So the one from oranges and the one from pine trees. And you can see that we've got a white precipitate. And these are 1%, so very dilute solutions. They're not even viscous. Until you mix both enantiomers together and one little more swirl, you can kind of see that little bubble. It kind of gels up. And at this point, this could just be that they somehow crashed out together. But we were optimistic that these might actually have co-crystallized. And so you can shoot X-rays at these and immediately see that these are crystalline materials. And we were fortunate enough to have a collaborator in Italy, so Fenizio Ariyama, was able to figure out the crystal structure of a crystalline sample of the mixture. And so it's a little hard to see here. These are the chains of the polymer, and we're going to now color code. One enantiomer is blue, and behind is another chain, and you can see this enantiomer packs kind of exactly in the void volume of where this one below has. And these molecules, they stack now in layers, and so one enantiomer makes a layer, the other enantiomer fits above. And my crystallographer did one last turn here that makes you a little dizzy, but so we're back where we started. So you can see this one here has a ring, this one here has a ring, and they basically can zipper together and interdigitate in a way that they don't do if you only have one enantiomer. And you might say, well, what's that good for? Well, first of all, these are really high melting. Actually, they're too high melting. They're so high that if you try to melt the polymer, it decomposes the polymer, so it's over about 180 degrees. But it's really interesting as a supermolecular synthon that we're trying to grow and put on different molecules as a way to bring them together and make supermolecular assemblies through these, what I think are some pretty interesting stereocomplexations. So, so that's just a little aside that I wanted to tell you about. I'm going to move on now to a very different type of polymer, and this is a great example of what I'll call biomimicry. This polymer is it's made by nature, and people found a long time ago that you could isolate this from various types of bacteria and algae, where the bacteria make this plastic as a way to store energy. So when times are good, there's plenty of food. The bacteria will take sugar, for example, from corn, and the bacteria grow granules of the plastic to the point where at the end of the fermentation, about 90% of the weight of the bacteria is plastic. And so you can then extract that with an organic solvent, and you pull out this polymer. And looking at this polymer, if you know polypropylene, so there's a propylene unit. Basically, there's a CO2 unit. There's a propylene unit. This looks kind of like polypropylene. It's even got a better dipole than polypropylene. And so you wouldn't be surprised if I told you it's semicrystalline like polypropylene. And it has a melting point that's also 180 degrees versus about 165 degrees. It's almost you can think of it as a biodegradable replacement for polypropylene. Since it's made by nature, nature's figured out how to make it magically disappear in reasonable time frames, unlike polypropylene that if it gets into the environment will last for decades or even longer. So these have been made for a while. There was a company in Cambridge called Metabolics. And my understanding is that I think their stock is now at zero. They worked for a long time to make these by fermentation. And the problem with this is that you first have to grow the corn, and that uses a lot of fossil fuel. You then have to have a very capitally intensive and energy intensive fermentation process. It's also slow. So yeah, it's really expensive fermenter, and you have to wait a long time. Ideally, it makes some polymer that you're hoping to sell, 50 cents a pound. We're not making some life-saving pharmaceutical compound, they're making plastic. And so these materials cost, I would say in the best case scenario, about an order of magnitude more than polypropylene. And unfortunately, there's only a certain number of customers that are willing to pay more for a plastic that they deem better for the environment. So, but this plastic is pretty awesome. And we thought that maybe if you could get away from a fermentation and go to organic chemistry to make this, you might be able to not only make this polymer and make it better and make it cheaper, but you could then tailor the structure. You could put on different substituents and do things that you can do with fermentation, but it takes a long time to be able to get the chemistries to work. So again, I'm going to pare this down to a single slide to show you the general strategy that we've used. So we've developed a class of catalysts that have a Lewis acid and a cobaltate anion. And this catalyst can bind to the epoxide and then basically insert a molecule CO into the less substituted carbon-oxygen bond, going from the 3-membered ring to the 4-member ring lactone. These are important for a lot of different applications. If you ring open these are structures that you would get from an alkyl condensation, building in stereocenters that are present in the epoxide monomers. But in this case, we actually wanted to take this, and you can imagine that if you can clip open that acyl oxygen and do that over and over, you can make the same polymer that nature makes, but you're doing it in a chemical reaction. So in this particular reaction, we developed a tandem catalyst system where the first catalyst converts the epoxide and CO to the lactone. And we can follow this by in situ infrared spectroscopy by looking at the carbonyl, and you can see the lactone grows really quickly and declines as the carbonyl shift for the polymer grows and levels off. And so at about 6 hours, if you open up your reactor, there's no epoxide or lactone, there's only left behind crystalline polymer. And so we've been looking at this as a way to try to make this type of polymer commercially. One thing that you might have noticed is that to make the natural polymer, these are perfectly isotactic, and they're chiral polymers, and so nature makes the R stereocenter. To do that, the easiest way to do that would be building the R center in the lactone, and then you would want to start with the R propylene oxide. And that stuff's pretty expensive. You can make it now. Jacobson has a beautiful way to do the hydrolysis of it enantioselectively, selectively, but you're actually burning half of the epoxide to make propylene glycol, and so immediately this would at best be twice as expensive as propylene oxide. And so we spent some time, so again, we can make this polymer from this lactone, from this epoxide, and the best way to do that now is you do a kinetic resolution where you would basically eat this up with water and make glycol, and then you would have optically active epoxide. And we thought maybe if you could come up with a higher value use of the unwanted enantiomer, then you could actually make this a lot more economical. And so what we decided to look at is a polymerization strategy. If you can take the racemic epoxide and develop a catalyst where the S enantiomer polymerizes, you're left with the R. The cool thing here is that this is a new-to-the-world polymer, but we've made some, and we know that it has properties that are almost as good as nylon. And so instead of throwing that away, we'd have a very valuable byproduct that might even be more valuable than the optically active epoxide that's left over. And from an academic standpoint, nobody had ever done this, and so we thought this would be a really good test for catalyst design strategies. Can we develop a catalyst that has very high levels of enantioselectivity for epoxide polymerization? And so I think this is the only one where I'm going to walk you through our design criteria for the catalyst. We thought that a bimetallic catalyst would be good so that a growing polymer chain on one metal would come over and attack an epoxide bound to an adjacent metal center. And modeling made that look like about 6 angstroms would be optimal. We needed to add an element of chirality, but also give these metals a little flexibility so that maybe to bring in the epoxide, you might have to open up the cleft. During attack, if you have a really rigid catalyst and you haven't designed it quite right, your activation barrier is going to be really high. And so this binol is good because it has some molecular flexibility between these two binol units. So we now need to pick some metals and carve out the ligand site around the different metals. And we opted to go with some cobalt salins, given our experience in making the epoxide CO2 polymers. And I should point out that this half is what the beautiful catalyst that Eric Jacobson's developed for the hydrolytic kinetic resolutions. So we developed some of these catalysts. If you're an inorganic chemist, we can show that we've made these by crystallography. You can actually measure the cobalt-cobalt separation. This is the cobalt-2 form. And you can also do computation and look at the energetics of pivoting around that aryl carbon-carbon bond. The most exciting thing about these is whether or not they actually do the catalysis. And I swear this is the very first catalyst we made. Usually we make one and it kind of works, and then you have to go back and do a lot of optimization. So this particular catalyst worked really, really well. So we add 4,000 equivalents of propylene oxide. We add in one equivalent of our catalyst. It turns out if you're not careful, these exotherm, because they make polymers so quickly, and epoxide ring opening is quite exothermic. So in about 15 minutes, this reaction was finished, even at low temperature. We looked at the product, and it went to about 50% yield, and the polymer made was very crystalline, which bodes well for a highly isotactic polymer and a very highly selective catalyst. To figure out the selectivity of the catalyst, there are two ways to do this. One is you look at the enantiomeric excess of the remaining epoxide as you go to completion. And a perfect catalyst would have a plot where the EE of the epoxide goes up and up and up, and at 50% you would hit the top. And we get data that are, so the yellow curve here, the best curve for infinity is yellow. Selectivity factor of the catalyst of 100, where it only makes one goof up per 100 units, is the kind of the pinkish curve here. And you can see the data within the area of the experiment. That point is actually beyond infinity. So it's really hard to measure exactly the conversion of a volatile epoxide. And so the better way to do this is you actually look at the tacticity of this polymer. And if your catalyst is really good, you shouldn't have any stereo defects. And so here we can look at the EE of the product, and the best fit is about 260 to 1, meaning this catalyst will eat up 260 of the S enantiomer before it makes a stereo mistake and goes for the wrong enantiomer. Not quite as good as most enzymes, but still, you make a polymer product that's almost perfect in its tacticity. So I wanted to show a video of this, and we had to use a bulkier epoxide because if you do these with a propylene oxide, sometimes the vials blow up because they get really hot and the gas expands. So this is a catalyst in solution, and we're injecting this much bulkier phenylglycidyl ether, and so you can see it inject. And so right now, again, the yellow is from the cobalt complex. We've added 1,000 equivalents of the epoxide. And this is a nice projector. You can start to see maybe that it's a little cloudy, and now you can really start to see that something's forming in there. This vial, by the way, is pretty hot because we just ate up about 500 equivalents of epoxide in about 30 seconds. And in case you can't quite see what's going on, we'll flip it over here. The little stir bar is trying to stir, but so that's polymer. We make this highly crystalline S enantiomer of the polymer. And then left behind in virtually 50% yield is the R enantiomer. So we're super excited about this catalyst for the reason that we started it is that we now have a great way to make optically active epoxides without kind of throwing away the other half of our material. We're finding that some of these chiral polypropylene oxides have, as I mentioned, properties that are as good as some engineering plastics, and they're way, way cheaper. So making nylon 6 and materials like that are quite expensive, and they're also not as easily degraded as a polyether in the environment. So we're now working on looking at this for other purposes. I do want to go back and show you one thing that I'm super excited about, and this might be from a real world standpoint one of the most important things we've done. We got into, and this is kind of a message for the students, you kind of get into an area and you might have a reason of doing it, but sometimes keep your eyes open because sometimes it's not until you get into an area of science and you realize, wow, okay, that was important, but this is even better. And this goes back to looking at carbonylating propylene oxide, and I just showed you all this work we had to do to put in a stereo center of controlled fashion on the propylene oxide. And some of you might say, like, well, what happens if you just leave the methyl group off and you go to ethylene oxide? Ethylene oxide is way more attractive as an economic epoxide for this reaction because you can get it from ethylene, and you can get ethylene if you want cheap. You get it from shale gas. If you want to incinerate the polymer and not worry about added CO2 to the atmosphere, you can take bio-derived ethanol, you can dehydrate that, and you can make a bio-derived ethylene oxide. Our catalyst works really, really well for this. As you imagine, there's no stereo centers that slow the catalyst down. We make propyolactone, and here you can make polypropyolactone. And this turns out is really important in finishes on furniture. And so if you go to IKEA, there are various types of furniture that you buy there where they use polypropyolactone. And right now they do it from ketene and formaldehyde. And if you can now make this from really cheap ethylene oxide and carbon monoxide, this is incredibly inexpensive, and this could be the world's cheapest polymer. Given that the CO is very cheap, that's from oxygen, and this is from probably the cheapest carbon-based building block. You can isomerize this, and you can make acrylic acid. That's currently made from propylene, used in water-absorbing materials. This process is a lot cheaper. The price of ethylene is cheaper than propylene, and the oxidation process to make acrylic acid from propylene results in a lot of byproducts that have to be removed. The final thing you can do is you can do a second carbonylation of the propyolactone and make C4 acids like succinic acid, succinic anhydride, and that goes into a really important class of biodegradable plastics that are mainly used in the agricultural industry. They don't have very good properties, but they're used for row covers, so you can grow your plants. But at the end of life, if you use polyethylene, that would be in the soil forever, and they want to use biodegradable plastics, and they don't really care that the properties are spectacular. It just has to kind of keep the weeds from growing. And so we're in the process of, we've developed a continuous flow plant at Novomer and are trying to now make this on a much larger scale. All right, so I've only got a few minutes left. So in the last 10 or 15 minutes, I want to spend time on on a topic that I never thought I would be talking about because it's very different than this catalyst development. So it has to do with plastic recycling. And as excited as I am about these bio-derived plastics that we're making, the reality is that 2/3 of the world's plastic are polyethylene and polypropylene, and they're super cheap and they're super good. And unless the government says like, oh, these are really bad if they get in the environment, you can't use them anymore, we're probably going to be using it for the foreseeable future. And so then the question is, well, if we're going to be making it and using it, what happens to it when we're done with it, right? We don't want it to get into the environment. If there's a way that you can recycle this even 1% more efficient than what we currently have, that's probably a bigger environmental impact than any of these biodegradable plastics that we've ever made. Because again, we've already got these plastics, and I don't think we're going to quit using them. And so my question to you is, when we're done with our water bottle, we're going to go find a nice blue bin and put it in the recycle bin. And so what percentage of plastic packaging materials are actually recycled?
Less than 10%.
And so, what was that?
Less than 10%.
So how many people saw this a few weeks ago? So this is C&E News, and it says only 14% of the plastic packaging waste gets recycled. So I actually think this is
in the US, or is that,
this is worldwide.
Zero.
Yeah, this is worldwide. And so I think this is wrong. And I was just putting my talk together last night. I pulled this off the web. So 14% of plastic packaging waste gets recycled. So the study that they get this from is from the Ellen MacArthur Foundation. And this is in the UK. And they look at, this is worldwide. And so 78 million tons of plastics are made. And this is just for food packaging, or for packaging. And according to them, and these numbers have been documented otherwise, about a third ends up in the environment. I hope that's wrong, because that just sounds awful. Obviously, different countries are different. In the US, a lot goes to landfill. They say overall worldwide about 40%. Some is incinerated. At least you're getting some energy out of it, and it doesn't end up in the environment as plastic pollution. And so 14%, I think, is what they mean is collected for recycling. It's not recycled. It's they pick it up, right? You put it in the bin, and somebody. And things are changing. You might have heard, we used to send it to China, and China finally said, we don't want your garbage anymore. And now there are all these recyclers in the US that are like, wow, this is really expensive. It was great when the Chinese would sort it out for us. And so now we've got places that instead of selling it to China and getting some money and getting recycled plastic, they're basically paying to have it put in a landfill. And so I think these numbers are changing as various recycling operations change the way they do things. So I'm going to briefly talk about what you have to do when you get this recycled plastic. Some of it just comes in, it's got like motor oil and crap in it, and they're like, we're not going to use this, so they get rid of that. 8% of the 14 goes into what they call cascaded recycling. It means you get a plastic cup, and you're not going to use it for a cup again. People don't want their food touching it, and so you make a 5-gallon bucket, and you can make it a little thicker if the properties aren't quite up to snuff, right? So it's a lower value application, and then there's 2% what are called closed loop recycling. It actually goes in to the same type application. So I would argue it's 2%, which is even more depressing than 14%. And you might wonder, like, well, why is that? And I've already started to kind of make a few hints at that. Let's take the two biggest plastics in the world, and these are the ones that I would think would probably be the easiest to mix together because they're both hydrocarbon, right? If you're an organic chemist and you take hexanes and pentane, are they going to mix? Yeah. So hey, why don't we just take polyethylene and polypropylene? We'll melt them together and we'll make some cool material. And it turns out that you actually get macrophase separation. These are if you take a 70%, 30% mixture, you get little globules of polypropylene, and the matrix here is polyethylene. And that's a TEM of that. And the reason that they don't mix is quite simple. These are large molecules. The delta S of mixing is about 0. These molecules, even though they're quite close, they have a positive delta H of mixing. And even I could do that math. Your delta G of mixing is going to be positive. So, and I've got a sample over here. This is, if you just took Chobani cups and milk jugs and melted it together, hoping to make some cool new material, it looks good, but It just snaps, right? If you make a milk jug out of that, you'll pick it up at the grocery store. You know, the handle falls off, or something bad's going to happen. So, so the bottom line is we have to sort this stuff out. And you go to things like polyesters and polyolefins, they really hate each other, right? These are very different molecules. So, okay, I'm not going to spend a ton of time on this, but you get post-consumer plastics. You start sorting things out. PVC sinks in water. PET and polyethylene can be separated from that. Polyethylene and polypropylene float. And this is about 2/3 of our plastics. So they have people trained to look at plastics and see what they are. But even better, down here is a movie at Municipal Recycling. They have conveyor belts, and they have infrared cameras. And if it shoots down and there's a carbonyl, like in a PET bottle, it then hits it with a little air jet, and it'll flip it up over into a polyester bin. And you can see this is not a perfect science, right? There's stuff flying everywhere. Every once in a while, there's like a newspaper that goes flying in there. And what do you do when you get a Tide bottle where the bottle is polyethylene and the cap is polypropylene, and part of the cap is welded on there? They're not going to have somebody cut it off, right? They're just going to throw it in there. And I thought this was kind of, this is what we used to have, and that's 5% of the plastic, and we can kind of throw that in and it's okay. But now they've gone to the concentrate, which is really good for shipping and less plastic. But now the cap is the same size, and now there's a whole bunch of polypropylene, and it really contaminates the feedstock stream even more. So it's this law of unintended consequences. Just when you think you've got everything worked out, some problems happen. So they kind of sort these things out, and you maybe get it mostly polyethylene or mostly polypropylene by sorting, but your properties are really going to suffer. And so we have this idea that instead of right now they have a certain amount that they incinerate, and these things go into cascaded recycling. So the dream is, can we throw in some magic foo-foo dust that instead of making it worse, makes it as good, or maybe we can even make it better, right? And instead of incinerating this, if we can get it to have reasonable properties, we don't burn it, but we can use it again. And there's obviously a lot of value in that. And from the environmental standpoint, it keeps stuff from basically being burnt. Okay, so super simple idea, and we're not the first to think of this. There are a number of molecules that people throw in to try to get polypropylene and polyethylene to like each other. If you're interested, these are some reviews, especially the top one. The molecule that we thought would be the perfect would be a block copolymer of polypropylene and polyethylene, with the idea you would have these region of polypropylene. And if you have a molecule where you have polypropylene and then you tie it together with polyethylene, and then you maybe have another block of polypropylene, at the interface of these macrophase separated materials, you would then be gluing those interfaces together. And instead of being able to rip it apart, almost like a perforated polymer, you would be gluing all these things together. And so we decided to look at some of these molecules, a little better idea of what, if you make a diblock polymer, you would have your polypropylene phase and your polyethylene phase. And a diblock would be a stitch. And maybe a stitch is strong, but many stitches would be better. And if you start to make things like tetrablock polymers, that could then weave back and forth over the interface. Not to mention, it can also then entangle into the polyethylene and polypropylene chains, not only just co-crystallizing, but actually commingling in a mechanical way with both polymers. And so we decided to test this idea. A number of people looked at diblocks, and they don't work very well, but we were hoping that maybe by looking at some new architectures, we might be able to impact performance. And I want to point out, so of the materials that are out there, you typically have to put 5 or 10% of the additive in. And you can do the math. You get about 5 cents a pound to be able to compatibilize at an economical time frame. And if your material is super expensive, there's no way you can afford to put 10% in. You have to get down at the 1% or a 0.5%, where it's really, really a very small additive to the polymer. Okay, so we decided to make these materials, and back to my catalyst background, we have developed a number of catalysts. These 4 on this side were catalysts that we've shown to be living and also make isotactic polypropylene. And what we wanted to do then is we made a modified version of the hafnium catalyst, which Tobin's done a lot of nice work with. In our case, we were able to first add propylene, grow a propylene block. We can then add ethylene. We can grow an ethylene block. And you can basically keep adding back and forth the two different monomers. And the catalyst will grow polymers over 500,000 in molecular weight. And you can control the block sizes by the amount of ethylene and propylene that you give it. If you're in the field of polymer chemistry, you know that there's this living plot. And so here is, as we make polymer, the molecular weight grows linearly. And here's a dye block where we swap to ethylene halfway through with overall about 150,000 molecular weight. So these are large molecular weight polymers. Okay, so the question is, do they work? And I'm going to show you one slide here and that kind of summarizes the work that we've done in this area. This is the little bar that I just showed you. If you just take polypropylene and polyethylene and try to melt them together, it's really crumbly, arguably having greatly inferior properties to the pure polymers. And the reason, again, for that is this macrophase separation. That's polypropylene. And the interface between the polyethylene matrix is very weak. And so think of this almost as like you're perforating your polymer and giving it the ability to kind of tear down through these surfaces. Now, if we make a tetrablock, and our nomenclature here is 60K means that's a 60,000 molecular weight block. That's an 80,000. Sometimes when you add gases, you add a little bit more. We're kind of aiming for about 70 to 80,000 for each block. And so this is a very large molecular weight polymer, and it's got 4 blocks. And if we add the tetrablock, and I've got a sample, and I'll actually pass this around if you want to look at it. You're probably saying like, well, of course he's not going to break it because it would look bad. So I'll give it to Tobin, see if he can break it.
I brought my scissors.
If you break it, don't tell anybody, okay? So
What is the weight? Oh, that's the weight.
that's just the label crinkling, yeah. Now he's really going to try. Okay, so 1%, that's just 1%. We now have, if you go to higher block structures, you can get down to part per thousand. And then the economics, I mean, you can make things that are really expensive when you're putting in such a small amount. And so stress strain plot, this is looking at elongation of the material and how hard it is to do it. If you just take that material, I had to blow it up here because it's so awful that you look at it cross-eyed and it falls apart. Polypropylene has this stress strain plot, polyethylene, and so you want something kind of like these materials. These are the pristine materials. When you add a dye block, it's better than adding nothing, but it's not particularly good. When you go to the tetra block, here's 5%. These materials are interesting because they're way more rigid than polyethylene, even though they're 70% polyethylene. And you can back off to 1% and still get a material. Usually you're not taking your milk jug and stretching it 4 times its original length, right? So these have really, really good properties. So we're super excited about this for 2 reasons. One is, if you can take materials that are currently being incinerated or materials that are being downgraded in their application and put in an economically viable amount of an additive, you now can use these materials over and over. The other thing that I'm excited about is, forget the recycling. If you can now make a milk jug that uses a third less material because you're making an alloy between polyethylene and polypropylene, there's less polymer to start with, there's less material to recycle, it's going to be cheaper for the consumer. And so there's definitely, I think, a recycling angle, but there's also a brand new kind of alloy of these 2 polymer angle. Okay, so I'm going to stop there and give you time for questions. A really quick overview, I've told you about a number of materials that we make from this. This is kind of another way to view my research program. We're taking these plentiful molecules like alkenes and epoxides and CO and CO2. And I started out by telling you some of the work we've done with aliphatic polycarbonates. I then moved on to tell you about making these lactones and making some biodegradable polyesters. And along the way, we kind of stumbled into this area of polyethers really as a way to make the optically active epoxides. Haven't told you anything about this area of polymerization of epoxides with cyclic anhydrides. And here you can get a range of materials from very soft, low TG materials to very crystalline materials to very high TG materials. And these are aliphatic polycarbonates, and so these all will biodegrade in the environment. We do a lot of work with polyolefins. I just told you about some of the block polymers, but we've got a big program on making thermoplastic elastomers. And then the kind of the emerging area over the last 5 to 10 years in my group is making polymers that are used for energy storage and conversion. And I really regret, my students are probably going to wonder what I spoke about when I came here. I would love to tell you about some of the work in fuel cells. And so this is the technology that went into Ecolectro to make a type of fuel cell membrane that allows you to use non-precious metals for fuel cells. At the same time, we're trying to make polymer electrolytes for batteries that have better conductivity than standard polymer electrolytes and also inhibit dendrite resistance so you can charge more effectively. Okay, so I'm going to stop there. Thanks to my really spectacular group of students at Cornell. And I'd especially like to thank you for the invitation to come here today. And I'd be glad to answer your questions.